Alright, today we're going to talk about counting principles. And so for 9.1, the first thing we need to address are the differences between discrete and continuous numbers. Discrete numbers are going to be whole numbers that we can count. Tangible things usually is the easiest way to think about it. So 1, 2, 3, 4, 5. And then continuous numbers are usually associated with some sort of measurement. So if you think of the numbers 1 and 2, in between 1 and 2 there's 1.5, and in between 1 and 1.5 there's 1.25, and so on and so forth. And so continuous is almost always associated with something that you can measure, and then we also deal with issues of precision or orders of magnitude. And as I said before, discrete refers to counting things like 3 boys, 4 cars. You would never have 3.5 boys. You would never have 4.5 cars. You would just count whole numbers is usually how I like to think of it. Where with continuous you can have like 7.35 meters, you could have 7.358 meters, and so on and so forth. So we distinguish these two types of methods for counting. For example, if you were to do some sort of probability of there being 5 seats on an airplane, you would never do 5.5. So with that in mind, if we look at discrete mathematics for a second, let's assume there are 3 objects A, B, and C, and we want to list those in distinguishable order. And so what I would do is my first choice would either be A, B, or C. Once I have chosen or selected A, then my remaining choices would be B, C, or C, B. And then if I apply that same logic to everything else, if I choose B first, then I would be left with A and C. So think of like putting 3 ping pong balls labeled A, B, and C in a bag. When I choose the first one, then I choose the second one, then I choose the third one. I could have a total of 6 possible arrangements, and the way that we figure out those possible arrangements is by using this tree diagram. It's a real nice way to kind of draw things out. This is the same way that you could calculate the probability of like a lottery. So if you have 45 ping pong balls that are labeled 1 through 45, and I choose 1 on the first one, then I have the remaining 44, and then I have the remaining 3, and there are some possible combinations. Well, it sure would be nice if there's a way that I could use some sort of multiplication principle, because just picture that factor or the tree diagram for the lottery numbers. It would be very big. So let's do a real application like Tennessee license plates, which have 3 letters and 3 digits, so it's 6 possible objects total, and of the 3 letters we have 26 letters, and of the 3 digits we have 10 digits, and so we have 26 possible letters and 10 possible digits we could choose from. Now, no restriction means with replacement. That means we can use the numbers over and over and over again. So on my first try I can have 26 letters. On the second try I can have 26 letters, and 26 and 26 times 10 times 10. So if I jump back to that last slide, what I wanted to show you is that we just multiplied to get our 6 possible outcomes. Now if we don't repeat, I can do 26, choose 1, then I have 25 remaining, and 24, and then the same with the digits. I have 10, then 9, then 8 remaining. It almost looks like factorial type of math, but it's not, and we'll show you a shortcut on that in just a second. But anyways, as you can see, depending on with or without replacement, it changes the total number of possible outcomes that I might have. With replacement, I'd have 17 million outcomes. Without replacement, I'd only have 11 million outcomes. So for example number 3, what we want to do is we want to count 9 different letters that can be formed from a word, and we want to figure out the possible outcome. So in other words, if I have the word dragonfly, how many different arrangements of the letters dragonfly can I rearrange and create words? And we'll ignore whether or not they're real words or in the dictionary. So on the first attempt I have 9 possibilities, then I choose 1, that leaves me with 8, then I choose another, that leaves me with 7, so we have 9 times 8 times 7 times 6 times 4 all the way down, which is 9 factorial, and that gives me 362,888 possible outcomes. However, if I use the word butterfly, I have 2 letters. I have T and T. Now that may not result in a new word. In other words, I might choose the first T and then the second T, and then on our next word we might choose the second T and then the first T. So I can respell the word butterfly by choosing the second T and then using the first T second. So it's not distinguishable, and so what we're looking for is distinguishable words. In other words, I can get the same combinations. Well, then in that case I would have 9 factorial over 2 factorial, and basically we're taking the possible outcomes and dividing it by the 2 factorial, or the combinations of the combinations of T. Well, let's use the word bumblebee. Bumblebee, same thing. I have 3 B's, so it's 9 factorial on top, divided by 3 factorial on the bottom. Then I have 3 E's, so I tack on another 3 factorial on the bottom. And so in our first word, dragonfly, we have many combinations, 362,000. And now with the word bumblebee, those outcomes have decreased significantly. Well, one thing that we could do is arrange these factorials in a way that we kind of have a shortcut. So, for example, if I were to say n objects take R at a time, in other words, I'm going to say 20 choose 5, or 16 choose 3. This is a permutation notation, and what that'll do is represent the total number of objects and the probability and combinations of those objects in a certain manner. So now for this particular formula, the order matters. How we arrange it, it matters. So if I have 6 people in a classroom and I choose 4, I get 6 over 2. And so 6 factorial over 2. Now that's without replacement. And that's how we would do that. So that's the permutation method. So now in example number 5, if we do a real life application, for example, I have 16 actors applying for 7 roles. Then I would plug that into the permutation, and these are the total possible combinations of the 7 actors that I would randomly choose. And in other words, I get 57,657,600 possible combinations of the 7 actors that I would randomly choose from the 16 actor pool. So we would say 16 choose 7 where order matters.